Hello everyone. Thanks for joining in. It's the last session of this year. It's my great pleasure to have Willie Neiswanger today. He is currently a postdoc at Stanford, and before that he did his PhD at CMU. Willie, take it from here. The floor is yours.
Great. Thanks so much for the intro, and thanks for inviting me to talk here. Realize it's at a different time, so thanks for being accommodating. I'm just gonna share my screen here. Okay, everyone can see this and hear me. Okay.
Yeah, perfect.
Great. Yeah. So just as some context, so this work I'm going to talk about is less on the applied side of AutoML, but it's more on the methodology of procedures that apply to expensive and possibly noisy black box functions. But there's many applications of this and problems involving these in AutoML, and some of the motivation I talk about is for automated machine learning procedures. I'm also interested in, just from people here, if you have any thoughts about different places that this could be applied, I'm interested to hear thoughts about that. We have a pretty small group, so I would say if there's questions at any point throughout, feel free to shout them out. Happy to discuss at the point when things are confusing, if they are, so please let me know. Okay, so this work I'm going to talk about was presented at ICML this year. It's work with my collaborators, Alex and Stefano from Stanford. And the one-sentence summary of this project is we're working on extending Bayesian optimization from estimating global optima of black box functions to estimating other function properties that are going to be defined by algorithms. Okay, so first I want to give a quick background on black box global optimization. So suppose that we have a noisy black box function f. So by black box, I mean we don't know the analytical form of f, but we can query f on an input x and then observe some output y. And we're going to assume that the observations of f are noisy. So y is some perturbed version of the function f at a given x. We're going to assume that each function query is costly, for example, in money, time, or maybe human labor. And the goal of this task is to estimate the location of the global optima of f, the goal of black box optimization, within a limited budget of queries. So let's say within a budget of t queries. So this task of black box global optimization has made example in the automated machine learning space. There's many applications in, for example, hyperparameter optimization or neural architecture search. More generally in systems auto-tuning, there's various applications for optimizing different computing systems, for example, for performance or metrics like latency or throughput or resource usage. In the sciences, there's various applications, for example, with some of the national labs that I've collaborated with in the past. They've used these techniques for optimizing different characteristics of particle accelerators or tokamak devices for plasma control and nuclear fusion, as well as applications in other areas of the sciences. For example, in materials discovery, such as catalyst design, as one of the pictures I have here, or battery charging protocols for better battery charging. Okay, and so a popular method to carry out this task of black box global optimization is called Bayesian optimization, with which many people here are familiar with. So Bayesian optimization, or BO, leverages a probabilistic model of f to sequentially choose queries, where the model can incorporate prior beliefs about f, for example, its smoothness or maybe some other behavior, and it can tell us where we're certain versus uncertain about f, which we can leverage to carry out sample efficient optimization. So the main motivation behind this work is that in a variety of real world tasks, there are many other properties of black box functions that we might also want to estimate beyond just global optima. So I'm going to give some examples here and applications of them. So in different variations of optimization, there's some properties beyond just global optima that we might want to estimate, some other types of optima, for example, local optima with respect to some initialization point, or maybe the top k optima properly defined of a given function. You see this in machine learning model training or hyperparameter optimization, neural architecture search, systems tuning. In tasks of multi-objective optimization, we often want to estimate the Pareto frontier over some multi-objective landscape. In level set estimation, we often want to estimate certain properties such as the sub-level set or the super-level set of a function. So this is the over a domain, it's the subset of points in that domain whose value is below a threshold or above a threshold. In different types of search tasks, we often want to find the subset of our domain that has values that matches a certain criteria. So we want to find a subset of our domain, which we can view as a certain type of property of this function. In phase identification, we want to estimate either boundaries or partitions of a function. In root finding, we want to find the roots of a function. In quadrature, we want to estimate integrals or expectations or averages of a function. There are certain times where we have a function defined over nodes or edges of a network, and we want to estimate properties of the network, for example, shortest paths and graphs or other graph properties. And finally, there's, for example, classic tasks of sensor placement, where we want to estimate the function value at a predefined set of locations. Okay, so in general, our goal is going to be to develop methods to estimate a broad set of function properties within a limited budget of queries using probabilistic models. So we can view this as sort of a generalization of Bayesian optimization to other function properties beyond global optima. So the first question we tried to tackle in this project is, how do we formalize this, this notion of other function properties? And we're going to do this through the use of algorithms. So note that if you have a given function property of interest, there often exists some effective algorithm for either computing or numerically approximating this property if you were to ignore a budget constraint. So as an example, say a property that we care about estimating is the local optima of a function f with respect to some initialization point. So what you can do is you can run a local optimization algorithm, for example, gradient descent or the Nelder-Mead method or an evolutionary algorithm, where in general, how many of these local optimization algorithms work is they initialize at some point, take a sequence of queries as you run your local minimizer, which converge to some local minima, and then you either return the final query or the lowest value query as your output. So this is some algorithm that returns the local optima property, local minima in this case, as an output. Or as another example, say the property we're interested in is a super level set of F. So in particular, let's suppose we have a discrete space of items. So we have some domain where we have a set of blue dots here representing our discrete domain. And suppose we want the subset of these points whose value is above a given specified threshold under the black box function. So an algorithm that we can use to compute this property is we can just scan through each of these blue points here. For each one, we query its value on the black box function. And then we take the subset of points whose value is above the threshold and return this subset of points. So that's an algorithm that returns the super level set of F over this domain as an output. Just a final example, suppose a property we're interested in is an integral or an expectation of F. An algorithm we could run is a numerical integration algorithm. For example, rectangular or trapezoidal approximation, where essentially you take a sequence of queries over a subset of your domain that you want to integrate over, typically over some sort of grid. And for each of these, you can construct a numerical approximation to the integral, which you can return. So in general, we're going to define a computable function property to be the output of a given algorithm A if we were to run this algorithm A on our black box function F. Okay, so each of these previous properties I mentioned are all computable function properties. For example, local optima or integrals, level sets, Pareto frontiers, partitions, etc. Because there exists an algorithm that you could run on the black box function that returns the property as output. And I'm going to define the task of Bayesian Algorithm Execution, or BAX, to be the task of estimating a computable function property, or equivalently estimating the output of a given algorithm A using a limited budget of queries. So for example, using only a budget of T queries to F, even if the algorithm A that produces the property requires far more than T queries. So even if the algorithm A can't run within a limited budget of queries. Okay, so note that we're defining a function property in terms of an algorithm. So there's two main reasons we do this. The first reason is because it gives a very sort of flexible and fine-grained way to define function properties. Just by changing details of the algorithm, you can slightly change your definition of the property. It's very precisely defined. And second of all, we're going to use this algorithm in our procedure to estimate these properties, which I'll talk about in a second. Okay, so let's get into methods for Bayesian algorithm execution. How do we actually carry this out? So I'm going to present an information-based method for BAX called InfoBAX, which is based on information-based methods for Bayesian optimization. So just as some background, so there's a number of algorithms for Bayesian optimization that rely on different acquisition functions that many people here are probably familiar with, for example, expected improvement or upper confidence bound, UCB. There's also a few methods of Bayesian optimization that are information-based, for example, entropy search or predictive entropy search or max value entropy search. And each of these methods are rooted in Bayesian optimal experimental design, BOED, where the just very high level idea behind BOED is, let's suppose you have a model with an unknown parameter of interest. You want to choose experiments that most reduce the uncertainty about this parameter, where uncertainty is often taken to be the entropy of the posterior distribution over this parameter. And these entropy search Bayesian optimization methods sort of follow this framework when they run. So to describe our InfoBAX method, I'm first going to describe the information-based Bayesian optimization methods, and then I'm going to extend it to information-based BAX. Okay, so first the broad algorithm for Bayesian optimization, including information-based Bayesian optimization, is the following. As input, you have a data set D, which is a data set of XY pairs, function observations, could be the empty set. And you also assume as input that you have a model for your function F. So let's suppose a prior distribution over functions. And then for a sequence of T iterations, you do the following. You first optimize an acquisition function to choose the next point to query your black box function. So an acquisition function is something that aims to capture the value of querying your function F at a given input X. And it's defined using our probabilistic model. And again, by optimizing this, you've chosen the point that you think has the most value, so it chooses the next point to query. You then query your function F on this input X, you observe an output Y, and you add this XY pair to your data set, and then you iterate. Okay, so visualizing this, let's suppose that we have an unknown black box function F, which is this thick black line here, and we have a data set of XY pairs, in this case, just 6 observations from this black box function. Given this set of observations, we can infer what is our black box function F using some probabilistic model. So here I've, by this gray band, I've denoted the posterior distribution over the function F, and I've taken a number of samples from this posterior distribution as these colored lines here. So each of these lines represents what is a plausible function under our model. Based on this posterior distribution, based on our probabilistic model of F, we can then define an acquisition function, which I've denoted here as alpha sub t, as this blue line, which again aims to capture the value that we think we get from querying our input domain on this x-axis here at any point. And then we optimize this acquisition function, yields the next point to query. We query our black box function, and then we add this new XY pair to our data set. Okay, so the key step here is line 2. It's defining and optimizing this acquisition function, alpha sub t. So looking at what this acquisition function is doing for information-based Bayesian optimization. So go back to this image of our probabilistic model of F given our data set, where we have, I'm plotting here the posterior function samples. So you can consider basically the global optima of each of these posterior function samples, which I'm going to draw as red dots here on the screen. So you can consider that there's actually a posterior distribution over global optima that's sort of induced or derived from our probabilistic model over functions. And you can think of each of these red dots as sort of a draw from this posterior distribution over global optima. And I'm going to denote these as this distribution as P of X star given our data set. Okay, so this leads to the acquisition function that's used in information-based Bayesian optimization, in particular the entropy search or predictive entropy search acquisition functions, which are the following, and I'll go through the terms here. So this is the acquisition function for a given input X, which is defined to be the difference of 2 terms. The first one is the entropy of the posterior distribution over global optima X star. So intuitively, that's the entropy or the uncertainty over this distribution, your current understanding of where the global optima is, minus the expected entropy of the posterior distribution over the global optima X star. if we were to make a query at a given input X and observe the output Y, which we don't know, but we have can hypothesize according to our model what it is. Okay, so this is the expected information gain acquisition function. It's the expected decrease in entropy if we were to query F at a given input X. And there exists a pretty clever way to compute it and then optimize it from work on predictive entropy search, which is the following. It breaks down this procedure into two stages, a before acquisition optimization stage and then during acquisition optimization. So before acquisition optimization, you want to generate posterior samples of your global Optima X star. So typically what you do in practice is you run some global optimization algorithm on posterior function samples to essentially compute these red dots, these samples from the posterior distribution over global Optima. And then the second stage is during acquisition optimization. And you store or you cache these samples from the global Optima that you compute. And then the second stage during acquisition optimization, for any X, you can then approximate the expected information gain alpha sub t of X using these set of samples that you've previously stored. And since you can do this for any X, you can essentially iterate over X in some procedure and optimize the acquisition function in a cheap manner. So the key computational benefit here is that you're only running this procedure on posterior function samples once before you do acquisition optimization. So then during the iterative acquisition optimization procedure, it's a lot cheaper because you're just using these samples that you stored. Okay, so that previous work that I just described was existing work on information-based Bayesian optimization. And now I want to describe the new work that we've done on our acquisition function for information-based BAX. So recall the goal of Bayesian algorithm execution is to estimate a computable function property using a limited budget of queries, or equivalently to estimate the output of an algorithm A that's associated with the computable function property, again, using a limited budget of queries. So similar to information-based Bayesian optimization, we're going to take a BOED approach where I'm going to define a few terms here. So denote the output of our algorithm A, or equivalently the computable function property as O sub A. And we're going to care about the posterior over this output that comes from our probabilistic model condition on the data that we've observed so far, and in particular, the entropy of the posterior distribution over the algorithm output. So we're going to want to make queries to best reduce this entropy or this uncertainty over algorithm output at each iteration. Similar to the previous case, we can also define an expected information gain acquisition function for our InfoBAX setting. So let me describe the terms here. For a given X, we again have two terms. The first one is the entropy of the posterior distribution over algorithm output minus the expected entropy of the posterior distribution over algorithm output if we were to make a query at a given input X and observe an observation Y at that X. So this is the expected decrease in entropy or the expected decrease in uncertainty about the algorithm output if we were to query F at a given X. So how do we compute and optimize this expression? First, I need to define one more thing. So we're going to define the execution path of an algorithm A as the sequence of queries, so the sequence of XY pairs that the algorithm A would have made if you were to run it on the black box function F. So for example, taking the two examples of algorithms that specify a property that I described before, if you take local optimization algorithm, what it does is it initializes at some point, it takes a sequence of queries and then eventually converges and returns one of these final points as output. So you can think of these pink dots here, the queries that it makes, as the execution path of that algorithm. Or equivalently for the super level set example, we iterate through each of these blue dots, query the function at each of these blue dots, and then return the subset of points that are above the threshold. Again, you can think of the sequence of pink dots here as the execution path of this particular algorithm. So note that we don't know the true execution path on the true black box function F, since we're not intending to run our algorithm A on F. This we're assuming requires too many queries according to our limited budget. However, if we have a model for F, if we have a posterior distribution over Fs, we have a derived posterior distribution over execution paths. And we're going to use that in our procedure. So visualizing this for a second, going back to our diagram here of a probabilistic model of F given our observations, where I've drawn these posterior function samples. Consider just the green posterior function sample here for a second. We can run our algorithm A on this posterior function sample and get an execution path, which I'm denoting with these red dots. This is just some arbitrary algorithm. Let's suppose this is maybe a local minimization algorithm or something. We can also do this for many posterior function samples. And in general, we can consider that there's a posterior distribution over execution paths that's implied by our probabilistic model. Okay, so how do we compute and then optimize the InfoBAX acquisition function? Similar to info-based BO, there's two stages, before acquisition optimization and then during acquisition optimization. So before acquisition optimization, we run our algorithm A on posterior function samples to get posterior samples of the execution path, and then we store these execution path samples. And then the second stage, during acquisition optimization, for any X in our domain, we can then approximate the expected information gain using these stored samples of the execution paths, which allows us, because we can compute it for any input X, allows us to optimize this acquisition function. So you'll note that this has a similar structure as information-based Bayesian optimization, but we've essentially in stage one replaced a global optimization algorithm with some arbitrary algorithm A that is associated with our computable function property. And in stage two, we've changed up the approximation of the expected information gain to be slightly different. But computationally, this has the same benefits, which is that we only need to run some algorithm on posterior function samples once before we begin the acquisition optimization procedure. And then we cache these samples. And then during the iterative acquisition optimization procedure, it's a lot more efficient because we can just use these stored samples. So in the paper, we have the math for computing the expected information gain given these sampled execution paths. Or have it also at the end of this talk if people here are interested in discussing through the math. But I guess the one thing to note is that for Gaussian processes, this can be computed pretty efficiently using some closed form formula that we have for Gaussian processes, and it can also be approximated for other types of probabilistic models through other Monte Carlo approximations. Okay, so the full InfoBAX algorithm looks similar to that Bayesian optimization algorithm I showed before. A couple differences are that for input, in addition to the data set and the prior distribution over functions, you also take an algorithm A that specifies your function property. Then for a sequence of T iterations, you again optimize your acquisition function to choose a point to query that point on the black box function, add your new XY pair to your data set. But for the acquisition function, it takes the algorithm as input. And again, there's 2 steps here for the acquisition optimization part. You first run the algorithm on posterior function samples, and then you optimize this acquisition function using the resulting sampled execution paths. Okay, so here's a one slide summary of the whole story I've said so far. So if there's anything that's not clear, this would be a great time to ask any questions or ask about anything that would help with clarity. So the one slide summary of the whole story, suppose we have a black box function F and some property of interest. This could be, for example, a level set or a inflection point of our function, or maybe an integral or a local minima. And suppose that this property is computable. So there exists an algorithm A, could be of any budget, but it returns this property as output. So our goal here in Bayesian algorithm execution is to estimate this property, the output of the algorithm A, with a minimal number of function queries. And as a solution to this task, we've described this InfoBAX procedure, which is a sequential algorithm, similar in structure to Bayesian optimization. Through a sequence of iterations, it optimizes an acquisition function and then uses that to query the function at a given point. Where this acquisition function, to optimize it, has 2 stages. First, a stage where we run our algorithm on posterior function samples and then a stage where we can approximate and iteratively optimize our expected information gain acquisition function. And as an output to this procedure, we return a posterior estimate of the property of interest, or equivalently a posterior estimate of the output of our algorithm A. Okay, so next I want to talk about some demos and applications of BAX, kind of just showing some intuition about what's going on and how you can use it for a few different areas. I think some of these are more, and some of these are less related to AutoML, but hopefully it'll maybe get some imagination flowing about where this could be applied. So I'm going to try to show it on a few different properties to kind of show the breadth of what we can estimate. The three ones I want to talk about first is a task of estimating shortest paths in graphs. So this is actually if we have a black box function over edges in a network. And the second two applications are both variants of optimization. So the first one is something that we're calling Bayesian local optimization. It's a method targeting of a black box function, and also estimating the top k optima as opposed to a single optima of a black box function. Okay, so first application, estimating shortest paths in graphs. As an overview, basically we're going to view graph traversal and search algorithms as defining a property of a black box function f that's defined on the weights in a graph. And our goal is then going to be to efficiently estimate this graph property. So as an example, we often have, there exists a variety of real world transportation networks. So for example, networks of roads, of railways, shipping or air. And suppose we want to find a shortest path from some location A to a location B in this network, where the shortest path depends on edge weights. You typically want to find the path that minimizes the sum of the edge weights between A and B. For example, these edge weights could correspond to traffic or road conditions, or maybe weather or shipping costs between two nodes in this network. And it can be often expensive to query or to access these edge weights. For example, you might need to measure traffic or road or weather conditions via a satellite or via some other instrumentation, or you might need to determine or access shipping costs, or maybe negotiate some shipping costs between two nodes in this network. And our goal here is going to be to adaptively query or access edge weights, and then infer weights of unobserved edges using some probabilistic model to efficiently estimate the shortest path in the network. Okay, so as a concrete example, let's suppose here that we have a grid-shaped graph. So something with 400 nodes and roughly 3,000 edges. It's a little bit hard to see, but each node here are these black circles, and each node is connected with its 8 neighbors through these little light lines here, or slightly less than 8 neighbors on the edges. We're going to assume here that the weights of each edge is given by a black box function f, which is this function here in green that I've overlaid on top of the graph. So specifically, suppose here that we've got this function over this 2D plane, and you can take any edge, look at its midpoint, and take the weight of that edge to be the value of the function at the midpoint. Okay, suppose our goal here is to know the shortest path between a start node, which is this purple square, and a goal node, which is this gold square. So I can tell you the answer. This is the shortest path that I'm drawing here on screen, is this black dashed line. You'll note that it sort of follows this valley of low weight edges here from the start to the goal node. As I mentioned before, you can view this shortest path as a property of the black box function that we've defined on the edge weights in this graph. Okay, so suppose that querying each weight is expensive in some way, for example, in our transportation network examples. So we're going to denote a query as a pink dot here. So how can we estimate the shortest path in this graph? So the straightforward thing to do is you can apply some classical algorithm for shortest path estimation. For example, Dijkstra's algorithm, which is sort of a graph traversal algorithm. So Dijkstra's algorithm will essentially start from the start node. It'll traverse the graph in some way, eventually reach the end node, and it'll take it basically needs to access or query a sequence of edge weights in order to execute. So what we can do is we can actually plot the sequence of queries that Dijkstra's algorithm makes as it executes. We're going to draw these as black dots here on our screen. So so this is a sequence of queries that Dijkstra's need in order to run. The pink query here is the final query that it makes. I'm denoting the output of Dijkstra's algorithm as this blue curve here. You'll see that this blue line exactly overlaps our ground truth shortest path because it computes this property exactly. The issue, however, is that this requires over 430 queries to execute. So, intuitively speaking, if we have some sort of probabilistic model, if we have some sort of amount of queries done, and then we have a probabilistic model about edge weights in this graph, it seems like maybe we don't need to take, every single query. Maybe we're taking a lot of redundant queries that if we have some prior beliefs about our unknown function, we can maybe bypass. Maybe we can also do a different order of queries in order to quickly get some sort of decent estimate about the shortest path without following Dijkstra's algorithm exactly. That's sort of the intuition here. So instead, let's try a different strategy. Suppose we take a small set of edge weights. For example, here I've showed you 30 uniform random samples over this domain. What we could try to do is we could try to observe these edge weights, infer the black box function over edge weights here, given these observations, and then try to infer the shortest path from these observations. So in particular, I'm going to do the following. I'm going to use the model to infer our function f. In particular, just a Gaussian process here, given our set of queries. And then I'm going to run Dijkstra's algorithm on the posterior function samples to see what is our induced distribution over the output, over the shortest paths that we have from this set of queries. So if I do this, I get the following. I'm plotting 30 samples of the shortest path that we get from this set of observations, as each one's a light blue line. You can see where the lines overlap. We have sort of a darker blue line here. And as you can see, this gives a pretty bad estimate of the shortest path. We've got some blue lines that try to go directly from the purple to the gold square along the top. And in general, it's very diffuse. We have not a clear idea of what the shortest path is in this graph based on the set of queries. So what happens if we were to bump up this uniform random sample significantly? So what is the estimate after 100 uniform random queries? If we're to do that, we get the following estimate. You can see that this is better. This is starting to improve. It's got the general shape of the shortest path, and then it kind of follows this valley here. But it's still not great even after 100 queries. And sort of intuitively speaking, what's kind of the issue here? So you can see the issue is that we're taking a lot of queries that might not be very informative to the shortest path. For example, we have a good number of queries that are in parts of the over parts of the function that have maybe a high value when we really want to focus our attention on low value parts of the function where we have a small value. We also have maybe many redundant queries, so queries that are right next to each other when really we're not getting a lot of information by doing this. So what can we do instead? Our goal is basically to choose queries to best infer the shortest path or infer the output of Dijkstra's algorithm. And this is exactly what our procedure of InfoBAX, where Dijkstra's algorithm is that underlying algorithm A, would give us. So let's see the sequence of queries that's made when we run InfoBAX with Dijkstra's algorithm. And I'm just going to show if you iteratively follow the InfoBAX procedure, the black dots are the sequence of queries that are made, and then the blue lines are the sequence of posterior estimates over the output of Dijkstra's algorithm over the shortest path that you get while running. So we can see here a couple things. Generally the set of queries we're making is following the true shortest path, though it's not following exactly Dijkstra's algorithm sampling pattern, and it's also not exactly following the shortest path, but sampling to some degree outside of it. We can also see that we're not really sampling in the same order as Dijkstra's algorithm. We're starting at places where we have information about the shortest path, and then eventually converging down towards sort of the bottom of the U here. So after 100 queries, here's the estimate of the shortest path that we get through this sampling pattern. You can see here that it's almost a perfect approximation of the true shortest path. It might mess up still a little bit at one position here, maybe based on needing more samples, or maybe based on our sort of prior beliefs, our prior model here, which might be slightly misspecified, but it converges to the shortest path a lot faster than for example, our uniform random sample. And we can actually just compare the sampling patterns at 100 queries of random search versus Dijkstra's versus InfoBAX, where for Dijkstra's we've just cut this off after roughly a quarter of the way through, and then see what the overall estimate of the shortest path is. And we can see that only in InfoBAX do we most quickly get a good estimate of the shortest path using sort of this few number of queries. Okay, so let me move on to the second application here that I want to talk about. So the second thing I want to talk about is what we call Bayesian local optimization. So regular standard Bayesian optimization typically aims to estimate global optima of a function, at least strictly speaking, when you sort of apply the algorithm without certain modifications. However, there exist many local optimization algorithms that only aim to find a local optima with respect to some initialization point. So for example, gradient descent or evolutionary algorithms, or the Nelder-Mead method or simplex algorithm are all examples of this. And these algorithms can be very effective for certain settings. For example, in high dimensional spaces where we have very cheap queries, they can work quite well, but they do often require a very large number of queries. Sometimes they take many redundant queries. They're not trying to be the most sample efficient. And oftentimes they're not as effective in the cases where each query is very expensive. So what we want to do here, what we can do is basically use these local optimization algorithms within the InfoBAX procedure as our algorithm A. And what this does, if we do this, is basically yields local variants of Bayesian optimization that are parameterized by a given local optimization algorithm. So the overall intuition here is that we're trying to view this optimization procedure as trying to estimate the output of a local optimization algorithm given a limited budget of queries, rather than trying to estimate an optima directly given a limited budget of queries. So let's kind of give some more intuition visually here. So suppose we've got a two-dimensional function, pretty simple function with just 3 local optima, which I'm denoting as gold stars. We can run a certain evolutionary algorithm called an evolution strategy, where we initialize at some point in the space, take a sequence of queries, and it eventually converges to one of the 3 local minima in this case. And after 208 queries, it has converged, and I'm returning the output of this algorithm as this gold star here. So this is what you get when you run an evolution strategy on this function. Let's compare this against a couple of more sample efficient sampling methods. So on the left, and this is all after 18 queries here, I'm showing random search, where we just sample uniformly over the space. We can see that the queries are very spread out. Gold star denotes the estimate of the minima after 18 queries. We can compare the sampling pattern here with max value entropy search. So this is a global Bayesian optimization method, again, one of the information-based methods that's really targeting estimating what is the global minima of the space. We can see here that the samples are indeed starting to concentrate around good low value function regions in the space. I say where regions where the function is is low. However, you see that these points are converging around multiple of the local optima here, as it starts to try to figure out what is the best point globally in the space. Compared with sort of the behavior of InfoBAX when we use this evolution strategy as the underlying algorithm A. What this does is it really converges to only one of the 3 local optima, and then doesn't really try to explore beyond this point. It really tries to focus queries at only one of the 3 local optima. And you can see here that similar to the Dijkstra's algorithm example that we just showed, essentially the sampling pattern is fairly similar to the underlying algorithm, the evolution strategy. It's just a lot more sparse in that we're incorporating our probabilistic model about the underlying function into the set of queries that we take. Okay, so let me just show a quick video of the sequence of queries that we make, running our Bayesian local optimization algorithm on this toy function here. Just get this to play. Okay, so we see the key thing is that it sort of converges to one of the three local optima and then continues to sample around there, trying to get as much information as possible about really just this one local optima. So we can also, extend this to slightly higher dimensional problems. So here I'm showing just two pretty simple Bayesian optimization benchmark functions, a 6-dimensional function and a 10-dimensional function. On the y-axis, I'm showing the value of the optima found at each iteration by each of these methods. Note the iteration here is on a log scale. Maybe the key line to look at here is this orange line, which is our evolutionary strategy. So we can see that this gets down to a pretty good point, but it takes a large number of iterations to get down here. And using InfoBAX with the evolution strategy, we can essentially achieve what the output of this method is, but using something like an order of magnitude fewer queries. And then just compared to a couple of baselines, such as some standard information-based global Bayesian optimization method, and these problems we also do quite well compared to these methods. So right now we've just done some initial implementation on using sort of evolution strategies as our underlying algorithm, but our goals in the future is to try to extend this methodology with a variety of other local optimizers here. Okay, final application I want to talk about is top K estimation. So suppose that we have a large set of items. For example, in science applications, suppose we have a set of 500 catalyst materials, which are often called bulks. And suppose that each item has an unknown value under an expensive black box function f. For example, each catalyst bulk has an activity level, which is expensive to measure. Typically, we have to run some expensive computer simulation in order to estimate the activity level in order to query our black box function on a given bulk. And suppose our goal is to determine the top K items in this set. For example, we might want to determine the top 10 catalysts that have the highest activity so that we can pass these top 10 off downstream to perhaps to other scientists who want to do additional experiments on these catalysts. Maybe they don't just want the top one, but they have a limited budget to do additional experiments, so they want the top K of our set. And you'll note that this is a distinct problem from both global optimization, which is where K is equal to 1, as well as to a related problem, but which is also different, which is level set estimation, which is the goal of trying to find all the items whose value is above a given threshold, as opposed to try to find the top K of those items. Okay, so we can run sort of a demo to visualize this. So suppose here that we've got 250 items over our space. And suppose that there is a black box function. Again, I'm showing in green, which captures the value of each of these items, just showing the contours of this function. Based on this function, we can plot what are the top 10 items that have the highest value under this function. I'm going to denote these as the gold stars here. So suppose we want to compute this property, we can run a simple algorithm that I call a scan and query algorithm, where you essentially scan through each of these items here, query its value on the function, and then sort based on their value and return the top K at the end. Let's run this algorithm on our set of items and function here. I'm going to, again, as in the previous examples, denote the set of queries as black dots and the outputs of this algorithm as blue squares. So we can see here, as expected, we've got a black dot over each one of our items, and the blue squares perfectly overlap with our gold stars because we can exactly compute the true top 10 items here in this case. Okay, the issue though is that this uses a number of queries that's equal to the number of items in this case, so 250 queries. So let's try out a new strategy. Suppose we were to make a few queries of the black box function in this space, and then based on these queries, we could try to estimate the underlying function and then try to infer what are the top 10 items based on what we think the function is. So if we're to take 10 queries uniform at randomly over the space, we get these set of queries here as black dots, and then we can basically apply a model to these queries and then infer what is our posterior distribution over top 10 items, which I've plotted on the screen. So the posterior samples of the top 10 items I'm showing as blue squares. Ideally, as before, we would want these blue squares to concentrate on top of the gold stars exactly. We can see here this is not the case. This is a pretty bad estimate based on this, this sample that we've got so far of the top 10 items. But what would happen if we bump up this this number of samples to 100 uniform random queries? So if we do that, we get the following. We could see it's starting to improve. We've got a few places, a few stars where we really do believe that the top 10 items are indeed, some of the top 10 items in a few cases here. However, we still have some true top 10 items that we don't think are part of the top 10. And then we've got some other items that we do think are part of the top 10, which are actually not. And intuitively, what's happening here is we're sort of, sampling in places that don't give us a lot of information. For example, we're not sampling in parts of the function that have high value. We're maybe not sampling over, certain items. So what we can instead do is try our InfoBAX procedure with this scan and query algorithm. So if we're to run this for 100 queries, we basically get a perfect estimate of these top 10 items in under 100 queries. The sort of intuition behind what InfoBAX is doing here is exploring the space fully, but it's trying to sample densely around high value items. So both in regions where we have items and in regions where the function is high. And based on that, you can actually estimate the top 10, the top 10 items here perfectly when in far fewer queries. Okay, so I'm just realizing now there's questions in the chat. Oh, can people still?
Yeah,
still
no,
hear?
it's fine. I think it was just on Xavier's side, so we can hear you fine.
Sounds great. Sounds great. We just got a few minutes here before the hour, so I just wanted to mention one final topic here, sort of as an aside, that's relevant to both the BAX and the BO methods that I've discussed, and also I think relevant more broadly, sort of in AutoML, for anything that involves uncertainty quantification, which is sort of a key methodology in a lot of areas, including AutoML. So I want to talk about some software tools that some collaborators and I are developing for uncertainty models. So the BAX and the BO procedures that we discussed all use, they're all based on certain predictive uncertainty models. So a model of the conditional distribution over output Y given an input X. So in the BAX paper, I focused on Gaussian process models, but we may wish to run similar procedures, similar BO or BAX procedures on a variety of different probabilistic models. And then notably, we might want to know if these models are good, if they give us good uncertainty estimates of the underlying black box function. Okay, so there's a lot of different types of uncertainty models that we might be interested in. There's sort of classic Bayesian models, such as Gaussian processes or various linear or nonlinear or hierarchical or other Bayesian models. There's different types of neural based models, for example, probabilistic neural networks or Bayesian neural networks or neural processes or otherwise. There's also other types of models, for example, ensembles or quantile regression or more. So, a question that basically we tried to help give an answer to in our work on the software is how can we easily assess the quality of predictive uncertainty? So just to kind of give some intuition here, we can visualize both point predictions from a sort of a method that returns points as predictions, as well as predictive uncertainties from a predictive uncertainty model in the following way. So suppose we've got a test set which has true scalar values. Let's assume it's a scalar regression problem here, where on the x-axis I'm showing the ground truth test points, and in the y-axis on the plot on the left I'm showing point predictions here, and on the right-hand plot I'm showing for each ground truth test point I'm showing a prediction with an uncertainty, where I'm showing these interval bars to capture uncertainty. But uncertainty can really be represented by, for example, an interval or a parametric distribution or a set of samples or more. Okay, so how can we empirically assess this predictive uncertainty? there's a few important criteria that we often care about, that's often discussed in sort of the literature. One is, the first is not a property of the uncertainty, but of either a point prediction or the mean of our predictive uncertainty, which is just the accuracy of our predictions. This is, accuracy is agnostic to uncertainty. A metric that we care about for uncertainty-based predictions is calibration. So is the predictive uncertainty distribution, is it under or is it overconfident? Again, calibration can be sort of agnostic to accuracy, which is to say that you could have really good calibration for a given predictive uncertainty model and low accuracy, or you could have really bad calibration and good accuracy, or they can both be good or they can both be bad. And then finally, sharpness. Sharpness means on average, how confident are the predictions? Overall, do we have very confident predictions? Overall, do we have very unsure broad predictions? And again, sharpness can be, you can have something that's sharp or not sharp, that's irrespective of calibration, and same with sharpness and accuracy. So in particular, calibration is sort of a very key one that we care about for predictive uncertainty. So I just wanted to discuss quick slide metrics for calibration. So suppose for each test point, we have a predictive uncertainty model that returns a 1 minus alpha interval, for example, 95% interval of the predictive distribution. So we say that our predictor is well calibrated if this 1 minus alpha interval covers a true value 1 minus alpha proportion of the time for all alpha. So just intuitively here, suppose we're plotting alpha equals 0.05, so 95% intervals. We ideally want this interval bar to cover the true value, which is to say to cover the yellow dashed 45-degree line 95% of the time. So roughly on the left in this well-calibrated case, that's what's happening. On the right, we've got an uncalibrated case where these interval bars are too small. So this is overconfident based on reality. This is an uncalibrated case. So what we can do for a metric for calibration is essentially scan alpha from 0 to 1. And for each of these, see what is the expected fraction of true values that's contained in the interval versus the observed fraction of true values from a validation set that is contained in the interval. This plots two curves between alpha from 0 to 1. We ideally want these two curves to be perfectly overlapping, but there's going to be some distance between them. And as an example, we can take the area between these two curves as a metric called the miscalibration area. So in general, some collaborators and I have released this toolbox to help provide some tools for various predictive uncertainty models in machine learning. This is called the Uncertainty Toolbox. It's a Python toolbox for predictive uncertainty quantification, calibration, metrics, and visualization. Feel free to check it out on GitHub. We're aiming to provide both sort of discussion and background on a lot of aspects of predictive uncertainty quantification, so including things like a glossary of terms and a relevant paper list, as well as implementation of various metrics, visualizations, and recalibration procedures, which try to tune up to improve the calibration of a predictive uncertainty model. Okay, so final slide, conclusion. In summary, for the bulk of this talk, I talked about extending Bayesian optimization from targeting global optima to targeting other function properties that are defined by algorithms. I've introduced the task of BAX, or Bayesian Algorithm Execution, and then the information-based procedure to carry out this task called InfoBAX. Feel free to check out our paper on arXiv, as well as the uncertainty toolbox for aspects of uncertainty quantification and machine learning. And thanks very much for listening. We'll be glad to take some questions.